Okay, welcome everybody to our weekly weather discussion. We're next week we'll be back to a live discussion over in the fourth floor of the Went Library, and people who are taking AOS 141 and AOS 751 are of course required to attend. And then there's room for others if you want to show up if you happen to find yourself on campus. In the first week of the semester, you might recall Pete was able to come over and get a live stream of our discussion as we've been doing in the recent past. I expect there might be a similar situation next week. I can't speak for Pete, but I have a feeling that he'll be interested at least in doing that.
I can speak for Pete since I am Pete, and yes, I do plan on being there and making my best effort at streaming the recording. We got a hard no on using the wired connections in there. Apparently those are CAE wired connections. They don't want somebody else, a non-CAE managed laptop on there, but we should be able to do it through Eduroam, so hopefully it'll work.
Okay, great. Well, thanks, Pete. So I guess we'll be back to a live stream as I'd hoped next week. So, but if you are in the vicinity of the campus and would like to stop in, we're on the fourth floor of the Went Library. Right as you come off the staircase, you're right in the room. So there's no side room or anything like that. So I want to begin today's discussion with the infrared satellite movie of the last several hours over the continental United States and adjacent waters. It's been quite a week. Well, actually, the last 10 days have been quite amazing. This beast up here in the central now Labrador Sea that's spinning around still quite mildly is former Hurricane Teddy. And Teddy, as late as Tuesday and Wednesday, was a major hurricane. Well, I should say a hurricane. Major by the time you get to 40 degrees or further north. Any hurricane's major, but it was a Category 1, bordering on a Category 2 hurricane east of the Gulf of Maine on Tuesday. And it had a warm core that was evident all the way up to 150 millibars. This was really a remarkable storm. And Michael sent me some images that you might have seen, all of you may have seen in the middle of the week, of the extratropical look that Teddy had at the time. And the reason it had an extratropical look, even though it was still a tropical cyclone, is because it intersected a really extended cold front that was extending almost from Reykjavik down to about Raleigh, North Carolina by the time Teddy intercepted it on its southern end. And it distorted that, not only the thermal field, but the associated cloud field, and really took on an extratropical look to it on Tuesday and Wednesday. But it was not extratropical on those days. It was still very discernible tropical storm. It's clearly now extratropical as it spins around to its demise in the Labrador Sea, but not before kicking up waves and probably doing its part in ensuring that the North Atlantic deep convection continues, because you got to rake the winds over the ocean to get the evaporation and send that cold air plunging southward as part of the conveyor belt circulation. So the storms do a big part of that, and Teddy is one of them. Everywhere else over the continent, the weather is largely quite settled. It's a little bit showery, as we'll see on the radar in a minute, over the middle Atlantic states. This is quite an impressive mid-latitude cyclone sitting over northern Manitoba right now, and with its cloud streak on the cold front sliding to the south and west across Minnesota, and it will be invading our own state here over the next couple of days. But we still have a run at 80 degrees Fahrenheit for a high today, and as I mentioned last week, the earliest last 80-degree high in Madison's history was September 2nd, 1977. This year, we haven't seen 80 since September 4th. And my feeling is, at least for the next 2 weeks, if we get by today and tomorrow without reaching that mark, we won't do it until the second week earliest, second week of October. And then the all-time latest last 80 is October 23rd. So we're making a run at finding second place on the all-time chart for that weirdo measure of a particularly unusual fall. But it's not dampened the extent of the nice weather. The weather has been gorgeous, as all of us know, over the last, long period. I think yesterday's shower at about 4 to 5 o'clock was about the only rain we've seen in Madison in more than a week. So it's been a really beautiful late September, and we welcomed the equinox on Tuesday morning at 8:30 a.m. And so we are now a couple of days into the fall. So it's been pretty nice. And then further west, there's a cloud mass that's made its way onshore into British Columbia, also Washington and Oregon. It's raining heavily in some of the places in the Puget Sound. And this doesn't appear to be a cyclone, as I think you can see even from this oblique view, but it does have to its west a cloud streak that is apparently racing towards the east, and that's part of an extended zonal jet at about 40 degrees, 43 degrees north that characterizes at least the eastern half of the Pacific right now. And from that flow, there will be the generation of quite an impressive storm, which I'll talk about in some detail, leading us into the forecast, but only in the Pacific Basin, that I think has the potential and appears to do this in the forecast panels to create a considerable perturbation to the flow downstream, leading us to what might be a really relatively record cold week for the first week of October. So all sorts of interesting things are about to happen. Michael, go ahead.
Yeah, I was going to say that just as you talk about that jet, I know you'll be looking at the Pacific image in a little bit. Just for those that were joined us last week, recall we were talking about this extended jet that was expected to develop. And so those models did a pretty remarkable job in capturing that evolution.
They did. And an extended jet is a rare beast because, you know, in the middle latitudes, the flow is subject to baroclinic instability, which means extended jets break up into little smaller jetlets and troughs and ridges invade. And so to have a long-term forecast where whatever the processes are that allow the maintenance of an extended jet, and I suspect they are strongly deformative processes more than vortex processes, the models know that in the modern era. And so that's, as you said, Michael, an excellent point. This is an excellent long-term forecast to nail such a feature, and we'll look at it in more detail in a minute. And as Michael pointed out, the tropics finally have calmed down a little bit in the Atlantic basin. It's been an incredible season. We had beta. This is the remnants, actually, of beta that's moving across the middle Atlantic states today. We've had beta. I don't think we've gone beyond that in the Greek alphabet yet, but we have a widespread, not too well organized convection in the south of Cuba and the Gulf of Mexico. And so, and then also into the Eastern Pacific. So not really anything particularly well organized. It's maybe the first period of a couple of days in a row where there hasn't been a well organized disturbance in the Pacific or Atlantic for a very long time. And we're only 10 days or so past the peak of the hurricane season. So we're not done. We're just hitting a hiatus, it looks like, at this present moment.
John, you're absolutely
Yeah.
correct. Looking at that image, it's clearly not debatable whether we're going to see anything else in the short term.
Yeah, that's right. That's right.
Debate.
Very nice. Very nice. You know, when you're like my dad, when you have to repeat your line twice, it didn't quite work out the way you'd hoped with the audience. Doesn't mean it wasn't a good joke. I just didn't get it. So now we'll go to the radar over the continental 48. And again, here in the eastern United States, the middle Atlantic states, we're seeing the remnants of beta, and it's still churning out some precipitation that's probably locally noteworthy, like in Norfolk and Richmond, and earlier in the day from Raleigh up to New Bern, North Carolina. And then the same thing in southern West Virginia, where the topography is a little more mountainous. So this is kind of a dreary but warm, moist day in southern West Virginia. And then here's some of the precipitation associated with the clouds tied to the Manitoba and Saskatchewan cyclone cutting across the Iron Ridge region here of northern Minnesota. And that's going to make its way eastward as the day progresses. We may see a shower sometime over the weekend from that. And then here in the Puget Sound, the front edge of this region of fairly substantial cloudiness and precipitation tied, I think, to the exit region of that zonal jet. And I'll show you that, give you some evidence for that supposition when we get to the upper level charts in just a minute. Okay. Other than that, just a few spots around the country with anything other than quite nice weather across the whole continental United States. Really nice day today. Here's the West Coast satellite image, and boy, it almost needs no words. Look at how fast these cloud elements, this is the infrared, look at how fast these cloud elements are moving across the northern Pacific Basin, right at, 40 degrees north. So, I mean, there's no question what latitude we're at. And this is a movie of, I think, just the last 4 or 5 hours. Yeah, 5 or 6 hours, actually. Let's see. Last 11 hours, every 10 minutes. So you can see a really rapid motion of all of these cloud elements. So there's a strong jet there. Notice on the cold air side, the northern side of it, there are little puffs of organized convective activity that go through discernible life cycles. This one comes off just off the Dutch harbor and then moves into the central Gulf of Alaska. It doesn't stay together very well. There seem to be other ones in the southern Bering Sea on the north side of the jet that have a little bit of punch. And then here's the state of Hawaii. Let's see if we can see it on the map. Maybe you can't see it so well, but it's right in this location. Here's the base of the trough over west of the date line. And little disturbances will grow out of this region. And I'm going to show you one of those in the range 2 to 3 day forecast on Vis 5D when we get there. But this is the broad environment within which the development that I'll talk about in some detail is going to occur. And even just looking at the infrared, one can see open cellular convective cells on the north side of this jet cloud street. And then to the south, you don't see that. You see broad patches of stratus clouds. And this indicates a big difference in the stratification of the column across the jet, which make good physical sense. On the poleward side of the jet, the air is colder at every level. And yet the ocean temperature isn't modified greatly by the presence of that transient cold air. So the stability is quite low. And it's easy to pop up these cumuliform clouds. Some of them drop little pea-sized hail, even though they're not very deep. And then on the warm side of the jet, it has to be warm because the vertical shear is from west to east, then you realize the stability is a completely different realm to the south of the jet. So very nice illustration of that. And the unsettled nature of the potentiality of unsettled weather to the north of the jet is something that will come into play as we move into the rest of the part of my discussion. So let's go now to the surface map across the continental U.S. And we'll start with our own region in the Great Lakes states. And we're still, sporting some reasonably high dew points, though lower than yesterday. We had dew points over 60 yesterday. And it's 57 today, right in the last hour. I guess this might be an hour old. It's not the most recent. I've got my presentation prepared a little bit earlier. And same at Milwaukee, 57 dew points and 71 and 68 for respective temperatures. The dew points are around 60 just about everywhere in the state. That's also true to the south. And as far south as even St. Louis, you poke above 60 degrees for dew points. So it's a pretty nice day across the central plains of the United States. And there's a really evident wind shift tied to, I think, that the cold frontal boundary that we saw in the satellite. And remember the rain stretching from about Duluth into the central part of Minnesota and in International Falls has moderate rain. So the eastern and northern half of Minnesota have precipitation and cloudiness. And that is precisely where the frontal boundary is. It's kind of very nicely illustrated here. All winds with a southerly and southeasterly component to the southern, to the down and right part of the frontal boundary. And then in the Dakotas, the flows are all from the northwest. And notice the dew point drops are into the 30s and 40s in some locations, 29 near Rapid City for a dew point. So it's really drier air coming in on the wings of this northwesterly wind behind the cold front. And if we go up toward Hudson Bay, we can find the center of the circulation. Let's see, I had that identified. Yeah, in Manitoba, we've got really roaring east-southeasterlies on the western shore of Hudson Bay near Churchill, Manitoba, and then 41 over 41. Somebody's late September fishing holiday has been ruined by this storm. I mean, nobody wants to be out on a boat at 41 over 41 with light rain. That's just about as bad as you can ask for. Pressure of 994. The lowest pressure I see reported is 987.8 with calm winds. So the central circulation is probably up in the northwestern part of Manitoba province. Pressure might be down below about 985 or 86. So it's a pretty intense cyclone. And then a very discernible cold front stretching to its south and west. And here are the northwesterlies or southwesterly winds that are behind the front. Notice the low dew points. And then the southeasterlies ahead of it with dew point increases on the order of 12 degrees. And temperatures about the same, even though it's cloudy. So these are being warmed by insulation. These are being kept down by cloudiness, but the dew points give it away. The front comes right around through like this. So it's a pretty nice feature in the central United States. Moderate rain at Bellingham. Maybe it's even heavy rain. I don't know if I am just missing the fourth dot there. Light rain in Seattle, Tacoma area, and then rain along the coast at Astoria. Some rain further up along the Columbia River, and it's raining also into eastern Washington. So widespread rain occurring in the Pacific Northwest all the way down about mid-coast of Oregon. And that is tied to, as you'll see in a minute, a fairly impressive jet streak that's just making its way on shore at about the Washington-Oregon border. So at least the northern half of this is well described as ascent resulting from being in the left exit region of the jet. And then down in the southern part of the western states, we don't see any smoke observations today, even though it's a limited set of observations across the state of California, as well as Nevada and Arizona. So no smoke plumes are signified by any of the surface obs today. That might be the first time in weeks where that's been true. And so let's see, we'll go over to the eastern United States. The remnants of beta light rains in a lot of places stretch away from central Raleigh, North Carolina, up into the Tidewater, Virginia and Maryland, and then in the western part of the state of North Carolina as well, and across the border into Tennessee. So this is and some in Kentucky. So that's the widespread region of mostly light precipitation. I don't think I see anything that says moderate anywhere at the present moment. And then it's warm and muggy down across the panhandle of Florida. Dew points are pretty high in the rest of the southeast, but not as high as they've been. Of course, 70 plus is the standard all the way through the summer and the early part of the fall down here. So we're looking at a slightly better than average day at a place like Jackson and other parts of Mississippi. So a pretty nice day around much of the country. Now we'll take a look at some of the upper level observations. I'll start at 500 millibars. And these are the ones Pete constructs for us, the so-called super Petes. And here's the continental U.S. and adjacent waters. And first, let's start over in the eastern part of the domain, where even at this time, this thing, though, is still clearly extratropical now. The upper minimum in geopotential is sitting right above the center of the circulation that we saw of the remnants of Teddy. And then there's a really nicely wrapped up thermal ridge that goes right into the center of Teddy across southern Greenland. And it starts about where my cursor is. Notice these are all the warmest air temperatures at 500 millibars. Sorry, I didn't mean to do that, but it works out. These are all the warmest temperatures at 500 millibars. That it signifies the presence of a deeply occluded structure. And my prior research with Andy Hullum suggested that when tropical storms transition to extratropical, they almost always have to adopt this structure because they're coming into the environment with very little vertical shear on top, and the only way to preserve that low vertical shear at the middle latitudes is to be occluded. And so that's why they're equivalent barotropic, and there isn't very much vertical shear on top of them. In a case where the storm lasts, this well, that's kind of how it works, it seems. And then here's a middle tropospheric upper trough over the central plains of Canada. Very sharp curvature, not only strong cyclonic curvature, but strong downstream anticyclonic curvature on the northwest shore of Hudson Bay. And that put together produces really strong upper divergence right in this region around Churchill, Manitoba, and that's about where the center of the surface circulation was at this time. So this is a nice illustration of the relationship between the surface low and about this location and its position relative to upper waviness. And then the main feature on the western United States and off to the Pacific is this zonal jet with a very intense zonal baroclinic zone. These isotherms in red are every 5 degrees. So you have a 15-degree contrast over this whole zone from the coast of Washington and Oregon well off to the date line, probably further west than that. So it's an impressive environment in which development might occur. And so I want to say just a few more things about that environment. Go ahead.
Yeah, so going back out to the Pacific, just south of the Aleutian Island chain, that small short wave, I think, is probably associated with that puff of clouds that you saw.
I think that's right.
Satellite.
Yeah, I think that's right, and it's minus 32, so it's you've got probably moist instability and a little bit of waviness, and that's enough to put some organization to that open cellular convection in that local region. I might have interrupted you, Michael. Sorry if you had something else.
No. That was just my point. Was that I think it's linking that feature with the satellite image.
Okay. Yeah, it's exactly right. Let's take a look at 300 millibars. I almost jumped ahead without doing that. And beautiful zonal jet. Look at the extent of that. I mean, think about it. From Massachusetts to Seattle is about 3,000 miles. This is at least a 3,000-mile transect of wind speeds at about 150 knots or higher at jet level. So if you're flying from Portland to Kazakhstan or someplace like that today, you're not going to go straight across the Pacific. You're going to go well to the north and around because you don't want to waste all your fuel fighting those headwinds. And that's important information, of course, if that's what you're doing. So an impressive jet there. And let's go to 200 to see what it looks like at that level. And it's just a little bit less intense. So this is a really deep, I think this is probably a super jet across the Pacific Basin. And I have some evidence to show that makes me think that I'll show you a little bit later. So this is a very impressive jet feature across the western part of the United States and then bleeding well westward into the Pacific. So it means business, let's put it that way. And one last level, we'll go to 850 because some of the threat of us getting to 80 is contained in the analysis that you can see here. So I'll zoom in on the middle part of the continent. And you can see the highest temperatures at 850 are in the immediate lee of the high terrain of Montana, Wyoming, Colorado, New Mexico, Texas. Here it is at Goodland, Kansas, 27 degrees at 850. So that's really cooking. It's 23 at Michael's hometown of Omaha. It's 26 at North Platte. and the 20-degree isotherm pushes northeastward into southwestern Minnesota, Worthington area. So this bubble of warm air is just about coincident with the geopotential height trough. And as you move further and further east, it's a little bit easier to believe that the geopotential height trough is discernible at the 850 millibar level. It's not so good over the mountains because 850 is in the ground. But when you get out to the eastern part of the Missouri River Valley, 850 is above the ground. So we can see a really nice lee-side trough structure here. And the main element of that structure is the coincidence of the geopotential height trough with the thermal ridge. And that's characteristic because both of those features are produced by the same physical process. And that is strong flow over the high terrain, forces subsidence in the lee. The air is compressed as it goes to higher pressure. It warms up, and that hydrostatically alters the geopotential, the mass distribution. It's especially discernible in the lower troposphere. So before we say any more about that, just remind you that the 500 millibar flow, which is about mountain height, is really strong across that high terrain of Montana, Wyoming, and northern Colorado at least. And that's why the lee-side trough structure is so prevalent in the northern portion of the plains and not so obvious over the southern plains. And that puts us, as you can see, however it's been constructed, we're in a region southwesterly flow at 850 millibars that is cutting across isotherms from temperatures well above 25 towards 12 in Green Bay. So this is really strong and sustained warm air advection in the lower part of the troposphere. With the sun out, it's not going to be hard to tap some of that warm air as it moved to the northeast towards us. So we have a relatively good chance of getting to 80 degrees today, probably the best chance of the entire week. And that's because we got a lee-side trough to our west. Okay. And then let's take a look at, I go to Alicia Bentley's maps because I can see the whole domain of basin at this one time. This is a 12-hour forecast from last night's 6Z run. And the reason I'm showing you the 6Z run is because when I go to Viz 5D, that's also what I'm going to use, the same forecast run of the GFS. So here's a forecast that's valid right about now, actually. And notice this little disturbance. It's 1,008 millibar surface cyclone right about at the date line. And then the dashed blue and red lines are thickness lines. They turn blue when you get to 540 decameters, which is traditionally the rain-snow boundary. So we also see the 250 millibar ice attacks. So this testifies to the extraordinary zonal extent of the jet off the coast of the Northwest. And then we could barely see, remember that little almost indiscernible troughiness in the satellite picture? That is on the eastern side of that trough. That's where this new little cyclone's developing. So I just want to click through these before we go to Viz 5D and show you something quite interesting about this storm. So here we go. Oh, what happened? Oh, I must have gone to the wrong thing. This is easily fixed. Okay, so here's the time at which I started. Wait a minute now. Yeah, okay, this is the time I started. Right there. So here's our cyclone developing. Look at how fast this development occurs in the Gulf of Alaska. Quite rapid development. That's, what is this, 1,000, so 96, 2, 8, 84, 80, 76, 72. This is like 964 millibars at Sunday 0Z. And then it gets maybe a little bit deeper, but watch what happens subsequently. That thing just about completely disappears in how many hours? Let's go back and find out. So this is where it's about 974, 48 hours in the forecast. And if I click to 72, I've got a 992 low. So I fill by 28 millibars in 4 hours. So this storm is almost extinguished, immediately extinguished during this last day from Sunday into Monday. And look what's happening to the upper level flow. If I go back and do the same thing again, notice when the storm is at its peak or just near its peak, we wanted to do it at 48 hours. That's its peak intensity. We've got this slightly cyclonically curved jet that is in the cyclones in the left region of that jet. It's a perfect position to be in it. Watch what happens to the jet over this 48-hour period. Oh, why is it turning anticyclonically? And when it does, the cyclone ends up being on the bald spot of the upper divergence. Because right at that point in an anticyclonically curved jet, you're going to have very little upper divergence of one sign or the other. Here, you're going to have a lot of upper divergence right in this location. So, and you've got your maximum intensity of the sea level pressure minimum. So there's a tremendous amount of boundary layer inflow into the cyclone just by the friction with the surface. And that mass, as long as there's an upper divergence valve, like a right-left exit region of a jet or a cyclonically curved flow, that mass can be evacuated out the top. But if you take away that divergence valve, and you'll do so if you turn that jet to be anticyclonic and you put the cyclone at the peak of that ridge in the anticyclonic flow, there's nothing to stop that cyclone from filling in rapidly, because all the air that's coming across the isobars because of friction is just going to pile up and never get out. And I think that's what's happening with this storm. So that's a really interesting aspect of this thing. And we did some work on this, Nathan Marsili, myself, and Justin McClay. I think Rhett Grauman was involved some years ago, and we learned some really interesting things about similarly rapidly decaying storms. And you might be tempted to think it's the orography. And in this case, it could be a substantial component of the storm just running into the jagged southern orography of Alaska. But we looked at storms that did the same thing, that were clearly throughout their entire life cycle well over the ocean. And so at least there's a strong dynamical signal of abrupt off of the upper divergence valve. And one way to do that is to turn the jet anticyclonically after it's been cyclonically curved. And that seems to be what's going on in this storm. Yeah.
Yeah, that's a really interesting point. I'm wondering, what factors do you think are causing the jet itself to turn anticyclonically, and could it be an upstream feature?
I don't know. I've been trying to think about that all morning long, and I did a little bit of work with, agiostrophic dynamics and whatnot, thinking about some basic issues. And it seems to me that if the jet speed decreases, there is a tendency for the agiostrophy to produce some ridging, and I'd have to explain that in another forum. But I'm beginning to think about how that might be connected. And it does appear in some of the other analyses that I looked at this morning that the jet speed does decrease. Now, the other thing that's countering that is there is a development, as you're kind of noting, there's a development at the base of this next extraordinary upper trough, and that development probably has a big cloud head associated with it. And if you page ahead, if that cloud head is diabatically altering the tropopause, that's going to be another factor that can lead to the rapid change of the tropopause, change of the jet, and building the ridge downstream. So I don't know if that's not a factor in this case. It certainly is a reasonable presumption, but I haven't been able to spend enough time to diagnose any of that yet. But it's an interesting case of how these things might work.
Yeah, I haven't looked at that myself in any depth, but I think I can show some evidence when we get to the forecast section of maybe the diabatic dosage you're talking about.
Yeah, okay, good. So that'll be fun to look at. And I just want to finish this discussion of this storm with a little bit of looking at Viz5D. So I hope this works well. And what I mean by hope it works well is I hope you can see some of the variables. Let's see. I'm going to zoom in on the domain as best I can so you can see what's going on. So again, this is a 060 run from last night of the GFS, and it's put in Viz5D format. I hope you can see the map boundaries. Alaska is right up in here, and then here's British Columbia coast, Vancouver Island, and then Washington, Oregon, and California. Okay, and it's this little disturbance right here. I'm just going to page through these, and you can see that cyclone right in here, this minimum in sea level pressure, is the storm of interest. And look at how fast it develops. Gets down to, in this simulation, 2840672. This is below 972 at this time, and that's 9Z on Sunday. Let's go to 12Z. It's down to 974-ish, and then it just like the other simulation, just disappears quite rapidly. Okay, how do I go backwards? I remember how to do this. Yeah. Okay, so this is pretty good. Okay, so that's one way to look at the storm. I wanted to do a couple of other things. I won't spend too much time here. One of them is, let's see, what did I have planned? I want to show you the potential vorticity associated with this development and over the same domain. So I'll go back to the beginning. And so here's the strong jet, of course, with the kind of zonally oriented PV. And for those who haven't seen Viz5D before, this is an iso surface of this variable. So you can see right underneath it, and that's pretty cool. And so that wall of PV that you can see right there from the south side now, and then from the north side here, that's where the jet is. And I can convince you of that by just putting the jet right on there. Here's the jet greater than 60 meters per second, and it hugs that wall. I mean, there's no question about it. It's right on that wall. So wherever you have a strong horizontal PV gradient in the upper troposphere, you're going to have a jet. And that's what we have in this case. I'll take the jet off in a minute. And then let me step forward a couple of times and notice what's happening here. We have this upper feature from the mid latitudes finding its way along the edge of this PV wall. And that conjunction is going to really mature. And I think at this point in particular, 06Z on Saturday, you can see a really intense and deep, these are colored by pressure, these PV isolines. You can see a really deep depression in the tropopause right in there. And I'm going to show you a cross section through that. First, note it's, I can do this another way. I'll put the pressure at a very high level on top of the map. So first, note the relationship spatially between the upper PV feature, which I'll show you again in another perspective, and the beginnings of the development of this surface cyclone. I'm sorry you can no longer see the map. I guess I can do that too. I'll get the map all the way to the top. So there's the map on top of it, if you can see it. Okay, so I'm going to cut a cross section right through here and see what the structure of that PV feature really is in the vertical. So that's right along that purple line, and I'm going to take the isosurface off so you can see it. I'll take the sea level pressure off also. So that's what the PV looks like in 3 dimensions. And that's pretty impressive. This is a steep wall. And if I put potential temperature on top of this cross section, you can see a really intense upper level front is associated with this, with a downward protrusion of the, with the downward protrusion of the PV. So right in this region, we have a really intense upper level front where the temperature goes from about 324 degrees Kelvin all the way to 290 or 300 across the boundary through that tropopause feature. And then there's a lower stratospheric front of almost equal intensity back in here, above the jet core. You don't know where the jet core is until I show you. There it is. So there's the jet core. These are every 10 meters per second, 30, 40, 50, 60, 70, 80. That's an 80 meter per second jet, and it looks like it's got both subtropical and polar components in the same vertical column. So this is a very intense jet feature, as we've seen already from the PV point of view. So if I put those things back on, there's the jet coming right through, and here's the PV picture 3D. So you can see how this all kind of goes together nicely. Okay. Now, if we take all of this stuff off, I'll leave the PV on, I guess, for a second. And then, I won't do that actually. Let's put just regular vorticity on I'm at 500 millibars. So this is the regular vorticity at 500 millibars. And I just want to show you that it's coincident with where the PV is. See where the red is? That's the highest values of the PV. If I take that off in the exact same location, that's where you have your strongest 500 millibar vorticity. So where this 500 millibar vorticity comes from is no mystery. It comes from the depression of the tropopause, and there it is in a perfect position to do some damage in the lower troposphere. And when I say damage, I mean this. I'm going to show you an proxy for the thermal wind, and now I'm going to zoom in. This is the potential temperature field at about 750 or so millibars. And then it's overlaid with the 500 millibar vorticity. So I'm looking at sort of the thermal wind and how it cuts across isopleths of vorticity. This is the largest value of the vorticity, the one where my cursor is. And so everywhere in this location, we have pretty strong PVA by the thermal wind, and that is a diagnostic for ascent and surface development. And if I put sea level pressure back on, that's where our cyclone's beginning to take shape, right in that location at this time, okay? And that's just as it should be. It's just beginning, though, to develop. It's only about 1,000 or 999 millibars. So let's step ahead a couple of times and see what this diagnostic pair looks like. This is at a later time, even more intense vorticity. And notice the gradient of the vorticity is extreme along this direction of the thermal wind, which will be parallel to these isotherms with colder air to its left. So it's going to be cutting from southwest to northeast. Let's put the sea level pressure back on again. And now we're really starting to see the development occurring. And remember, the strongest ascent at a moment is always ahead of the cyclone. So these will always lag a little bit. It's always up in this region. But now we're well below 1,000 millibars. This is 1,000 right here, and then 996, 992, 988. So we just had a lot of development there in the process of PVA by the thermal wind getting its act together. Step a couple more times ahead. We still have really strong development likely in this location just south of the Aleutian Islands. Here's the sea level pressure minimum, and now we're down into the 970 range, and it's really quite an impressive development. So this PV, and I'll show you the PV again, just so you get a sense of, look at how it's still correlated position-wise with where the 500 millibar vorticity is. If I take that off, you can see here's our 500 millibar maximum vorticity, and that's precisely where the tropopause PV is most intense. So it's a really nice illustration of the way things go together. And if I zoom out from my last statement, I just want to step through this, and you can see that tropopause depression gets even deeper, gets a little more red here, just south of Kodiak Island. But watch this ridginess disappear. So this ridginess here in the PV surface is effectively ridginess in the flow. Watch what happens. It almost wants to round the bend. This almost looks like an occluded structure getting itself together, but it just can't do it. It folds over itself anticyclonically. And when it does so, the upper level divergence valve for this first storm disappears, and it may be, as Michael suggested earlier, related to what's developing upstream. This is the secondary upper trough that spawns cyclone number 2. So there's a lot of interesting things going on over the weekend in the Gulf of Alaska, and quite a number of mysteries about how they all work together. But that's what I have for the discussion for the current weather pot today. So are there any comments or questions? Okay, if not, I'm going to hand over the screen to Michael.
Okay, thank you, John. Thanks for a great presentation.
Oh, wait a minute, what happened there? Oh, here it is. Okay.
All right. Well, good afternoon, and we're going to get started. Can everyone see the screen?
Yes.
Okay, so what I'm first starting with is from a NOAA website, from the Weather Prediction Center at NOAA. They have their 3 to 7 day hazards outlook, and there's a description about all of the hazards and what they're looking at, as you can see below here, but I'll just focus on a couple of things. The blue area you see over the center part of the Midwest is much below normal temperatures. So looking at their 30-year average of temperatures, it's expected from Kansas and Nebraska eastward and northeastward into the central Great Lakes, that they're going to be below normal temperatures in the week ahead, in the next 3 to 7 day period. You can see also extensive areas of brown on this map, which indicates severe drought conditions that exist along the west coast, where we saw some of the fires earlier this month, as well as into the southwestern United States and the Intermountain West. Then also over the northeastern part of the United States, which I hadn't actually been following too much. You can see those are areas, particularly coastal New England, from Rhode Island northward into interior parts of Maine. Fortunately, for some parts of that, they're expecting a period of heavy rain from New York State southwestward into just to the northeast of Harrisburg, Pennsylvania, and then again over South Carolina, a little bit of rain, heavy rain expected in the 3 to 7 day period. But that's the outlook for just over the next week ahead, the week ahead that we're looking at. If we go beyond that time period, and I want to make sure I get the right one, we can go to the 8 to 14 day hazards, and you can see this map changes considerably on this forecast mode, and this is focusing more on sort of temperature hazards.
Oh, yeah.
There's not much more in the precip, but this solid dark blue, and it's really important to understand how to interpret this map that you see over the southeastern United States and the Ohio Valley. That doesn't mean very cold, it just means a very high risk of below normal temperatures. So probabilities, I think, exceed 80% or 90% that it can be below normal in that region. But you can see basically from the central U.S. eastward, with the exception maybe southern Florida, is expected to be pretty risk of being below normal temperature-wise. While if you get to the southwestern part of the United States up into parts of California, there's a slight risk of above normal temperatures. And these forecasts are given in a probabilistic format. They're looking at weather prediction models, so they use that, but also statistical models that they use based on certain patterns that they've seen in the past. to come up with this particular forecast. So this is really an interesting sort of outlook. We're about to, we've had relatively mild weather the last couple of days, and we're now going to be turning to something that's going to be much colder. To begin to understand that, let's first of all look at we'll look at the dynamical tropopause maps. We're going to kind of telescope down to the short-range forecast for us in just a minute. But this is the dynamical tropopause map from 6-hour forecast valid at 18 days, so pretty close to our current time. You can see from this perspective, this extended jet, this extended area of fairly substantial north-south potential temperature gradient or variation along latitude scale, pretty close to, I guess, about 50 north or so, maybe 47 north. And this gradient is accompanied by, as we saw last week, fairly strong winds. So there's a jet here. And so this is really, the jet stream can be identified on these dynamical tropopause maps, or jets can be identified where you see regions of strong strong contrast in potential temperature on this so-called dynamical tropopause. To the south of the Aleutian Island chain, you can see a trough and if you will, a ridge in the potential temperatures, thermal ridge. That's you can see this H396, about 396 Kelvin in terms of potential temperature there, and a trough that's just to its west. And we'll see how this feature evolves over the next couple of days. This is the same feature Frank Martin was just looking at. As we step forward in time, you can see the amplification, somewhat of an amplification of the ridge, as the ridge basically gets advected downstream toward the Gulf of Alaska, and a deepening of this trough, potentially getting a little bit colder in the base of this trough, where it gets much more well-developed. And this is associated with a cyclogenesis event that we're going to be seeing occur at the surface during the same time period. But what's really interesting is, as this begins to evolve, as the trough itself amplifies in terms of its meridional extent, downstream ridge begins to develop. And as this continues to develop, you can see that downstream of the ridge, you can see cold air that's beginning along the dynamical tropopause, which is beginning to move southward over Montana. It's almost like someone cracking a whip and waves propagating along this jet, and that leads to the introduction of this beginning of this colder air mass that's going to be invading into North America. And it all starts from this Pacific cyclone that develops. As that system does, we can look at the time here. It's about 6 hours in the forecast. Notice going back into the Pacific south of the Gulf of Maine, that jet that we saw, and the trough there. If we go a little bit further in time, we can begin to see it's beginning to acquire some anicyclonic curvature. And there seems to be, although it's not evident, and like other comments from John Gregg, that there may be some diabatic heating that's going on that's helping to enhance this ridge. But it's interesting, just upstream of it, on the western side of the trough, you can also see these strong winds to the south that are helping to amplify the some sort of jet streak, very strong potential temperature gradient. It's refreshing. On the western side of the trough, sorry, this will, not sure why it decided to load, but it will come back up. My apologies. There we go. Let me go back to that time. Oops. So this, the change in the structure of the trough, it gets more anicyclonically curved. We were suggesting that might be related to the weakening of the surface cyclone. I'm wondering what's going on with this upstream trough and how it's being deformed over time that leads to the downstream development. But what you can see, the evolution of flow has really changed. The complexion of the flow. We have this nice straight jet across the Pacific into the Eastern Pacific, and then kind of petered out over North America. And now we have this fairly minimum potential temperature along the dynamic tropopause, which we'll see will be associated with a trough and a variable ridge over the western part of the United States and Eastern Pacific. And that's a fairly stable wave pattern that allows for continued intrusions of cold air. It's almost like a wintertime pattern beginning to set up, or certainly a late fall pattern setting up over North America. The final thing is, notice that the subtropics get dragged northward across the Gulf of Mexico as this pattern begins to evolve, with a big ridge developing just over New England and maritime Canada, Atlantic Canada, during the same time period. So this is the pattern that's going to emerge, and we'll look at this in the longer range forecast, but you can kind of get a sense, by looking at the Pacific, you can get a sense of some of the upstream things. And in case I don't get time at the end, I'll just advance this forward. Time-wise, we're looking at a week from today in this forecast. And again, deep trough over the ridge or west coast and a trough over eastern North America. You'll see that we come back to this extended jet pattern in the forecast by the time we get to next weekend. which is really interesting. So the models are forecasting another intrusion of this warmth across the Pacific. John?
Yeah, I was just going to say, I didn't go this far into the forecast to see the re-emergence of the zonal jet at the southern latitude of Oregon all the way out across the Pacific. I mean, it takes a giant perturbation this week, and then it reestablishes itself in the same location. That's pretty remarkable.
Yeah, so if I step ahead one, I think that gets me back to the beginning. That's where we started from. And this is, again, about 186, 192 hours out.
In some ways, it's even worse because you have higher tropopauses on the southern side than you did in the original zonal jet, and that's already 150 knots.
Right. So in the other maps that Pete has for the Pacific, I would guess, or you could probably even suggest that we're going to have a much stronger jet at the end, next weekend over the Pacific. So
I think I'd have to agree. Yeah.
Okay. So let's kind of zoom in.
Can I say something? I think the origins of this Pacific jet seem to be a lot of convection going on in South Asia, around the maritime continent, and that keeps reestablishing the jet across the Pacific, and it's just emanating from there, and then there's some cold air to the north, but it's mainly, I think, that warm high tropopause that's coming across that's creating the boundary that's forming the jet.
Right.
It's actually moving in two directions. There's easterly jet moving toward Africa to the south of the convection in South Asia, and then there's the westerly jet to the north. So there's two jets coming out of it, and this is the northern branch into the Pacific. So I thought I'd mention it.
Oh, thanks. Thanks for that. I wonder, is that? I'm not a. This is. Yeah, I mean, I don't know if Stephanie Henderson or others that study the MJO are on that might want to comment on this. In fact, enhanced convection of the Pacific, does it have anything to do with a certain phase of the MJO beginning to start up? I don't know if anyone can comment on that.
This is over maritime continent, so it's more the Indian Ocean.
Right. It's more.
The Pacific. Yeah.
Okay.
That's a really interesting idea, Greg and Michael, and if Angel or Stephanie are here, it'd be great to hear from them too. I agree. But the other thing that's conspicuous about mid to late September is that probably by this time, all of the prior winters and springs tropopause polar vortices are gone. They've been radiatively destroyed, and the reconstitution of new ones is just getting underway. So it might be the easiest time of the year for tropical convection emanating from one spot to produce a zonal jet in the Pacific, because there's nothing to perturb it from high latitudes. There's no disturbances yet.
So I wonder what then.
I think you're probably right on that.
So how do you get that acceleration across the Pacific? It's one thing to have the convection, but then what allows it to extend so rapidly downstream? Is it just the fact that they're going to be, on average, lower potential temperatures than north, so you get a nice gradient?
I guess so. I don't know. That's a good question. I don't know, because the jet exit. The circulation.
Can I take the screen for just a second to show you that on the other projection? I want to take the screen to show you what that jet looks like, how straight it is.
All right, let me get rid of this. There you go, Greg.
Okay. All right, so here's, let me go to the first. There's the jet as of midnight last night. And you can see how straight it is across the Pacific coming off of here. And then if you go forward for the next 8 days, nope, that's the last, forward, you can see that it breaks into waves.
Yeah, that's the first development. Yeah.
And then it reestablishes itself at the end. It's starting to anyway. But it's all coming off of here. It's a jet north of this over here. If I go and look at this, one more thing. I'll just look at this with the inertial stability. And that's interesting because you can really see it there too. So here's the first one. You can see in the shading here, here's the jet coming across the Pacific. Yeah. And this kind of funny shading over here is the easterly jet coming off of it. So both of these things, one going to the east and one going to the west, kind of anticyclonic out of this region right over here in the very maritime continent area. And so if you go forward on this, and what I also want to show is, see this plume of we looked at this last week, this plume of high tropopause air moving all the way across into the U.S. You see this long plume. That's a major feature here. And the jet is right on the top of it. This is that wall you were looking at, John.
Yeah.
And it's very straight. It's following a latitude circle almost. So if I go forward, there's where it ridges up. And you can see as it ridges up, this cyclone is forming in here. But you're looking at this warm air kind of, this high tropopause kind of pluming back over the top and just kind of mixing north. So my impression is, rather than cold air, what you're seeing is the warm or the high tropopause and cold air, it's stratosphere. But this mixing with the northern latitudes more than cold air coming from the north. I think that's exactly what's happening, and it's happening over here too. So you have this zonal jet, which probably becomes some kind of a baroclinic instability, and then breaks up into these waves. And we got 1, 2, 3, 4 waves here. So that seems to be what's happening. And I do think that you're right, that it's rooted in the tropical air. So I'll give you a screen back.
Okay. So you've seen this continental scale feature. Let's now move down toward the sort of local weather for us. So we're looking at, I'm getting some feedback, I guess. This is from the WRF model run that was done at 6C this morning, and you can see forecast of temperatures over the weekend. Actually, this may be the more recent one. Forecast for temperatures today to get into the mid 70s, and then perhaps even the low 80s on Saturday. If we look at the MM5 forecast, it's a little bit more modest with temperatures. Last hour we're at 73 at the airport. We'll check in just a moment what the current temperatures are, but about 23 degrees Celsius here, which puts us squarely in the mid 70s, and then get to 24 Celsius, which is 76 or so, 75, 76, at least in the MM5 forecast. Dew points in the climate, you'll notice it's going to be a little bit more, feeling a bit more muggy tomorrow relative to today. It's a nice breezy day outside today. And then we see temperatures and dew points beginning to kind of crash as we move into Sunday afternoon. And during that same time period, there is actually a possibility of a little bit of rain tomorrow evening. And the rain forecast is actually a tricky one. We're going to look at two different forecasts as time permits. One, the NAM, the other, the GFS. Because I think what's interesting is this rainfall that we're expected to see is going to be associated with the passage of a front, and it's a frontogenesis along the front, which I think is going to be responsible for the rain. If we look very quickly at the, this is a current map here. This is, again, a 90-kilometer forecast. You can see that Lee Trough, Professor Martin was noting earlier, see the strong warm advection on the east side of it. So warm thickness advection is going to warm us up. The rainfall associated with the remnants of our beta, and the rainfall along the west coast of the United States shows up pretty well in this particular short-range forecast. I'm going to jump ahead to this evening or early tomorrow morning. Again, you can see that thickness trough is kind of increasing its tilt as it gets advect, as the warm advection continues over us, well within the thermal ridge at this time. But you can see that trough or the thickness ridge you can see, but you can see the trough is now beginning to lag behind this, and it's beginning to take along the look of a cold front just to our west. And we'll look at a surface map to verify that in just a moment. But some rain expected in the northern part of our state over the weekend. Get to tomorrow afternoon. Okay, so this is around 1 o'clock tomorrow, or sorry, around noon tomorrow. You can see the thermal ridge is kind of all but kind of dissipated here as the flow is still southwest to our south, but we're actually now going to be getting into the trough passage. It's going to be sometime around this time tomorrow. And what we're going to note at the surface is dew points beginning to dry out a little bit as the winds turn more out of the northwest with the passage of this. But no precipitation, at least indicated on the model at this time. By tomorrow evening, we can see that weak wave begins to develop along this front, and we're still in sort of a neutral temperature, maybe slightly warm advection type of regime. I'll jump ahead to Sunday morning, but these forecasts you're going to see are very different. Cyclone begins to develops in this model run to the northeast of Green Bay over northern Lake Michigan. We get into cold advection, and our temperatures begin to fall with the precipitation. That's one forecast. I'm very quickly going to show you the forecast for the within the GFS. Go to the pivotal site. Again, same thermal ridge shows up in the forecast. I'm going to jump ahead to 24 hours. And warm advection again, that warm advection continues, but you can see this really strong and very prominent thermal ridge is no longer showing up on the map. We're still in warm advection. By tomorrow evening in the GFS, still decent temperature advection over us, and the rainfall in the northern part of the state. 42 hours into the forecast gets us to 6Z on Sunday morning. You can see the passage of the front. You see very clearly a wind shift. If you look at the 2-meter temperatures, or the temperature and wind bar, excuse me. Funky to use. Temperature and wind bars. You'll see really clearly a stark. And you can make out winds. You can see the westerly winds over us and over the northern part of the state, southwesterly winds along from Milwaukee and Janesville and southward. And so that's our temperature contrast. If you look at the relative humidity at this time, sorry, I meant to look at dew point, not relative humidity. That's more of an indicator of the temperature contrast, or the moisture content in the air. There's our temperature. Sorry about that. And then here's the dew point. Really a sharp gradient in dew point by the time we get to Sunday morning. So Sunday evening or Saturday evening into Sunday morning, we're going to get a wind shift, and then things are going to dry out really rapidly. Then the question is, when is the rainfall going to begin?
Yeah.
And this is really going to be a tricky thing. So in the GFS forecast, as we go forward in time, this is at 42 hours. This is Sunday morning, now at 12Z Sunday morning, so 6 a.m. Still dry over us with a northwest wind. Looks like a pretty pleasant day. And showers developing to our south during this time period. And that's right along the front where the front actually exists. If we go back to the NAM forecast for the same time period, we have a different forecast. Okay, we have the rain over us. In fact, I'll go back to Sunday morning. And we'll look at the 850 maps. You'll see that we're going to see this is associated with some weak frontogenesis, but it's different. The placement of it's a little bit different in the two forecasts. Here's the rain coming in on Sunday. So the NAM is a bit more aggressive with precipitation. The GFS and the WAR forecast were relatively dry during the same time period, but followed with the passage of the. So diagnosing that, or at least of what's happening with respect to temperatures and winds, let's look at 800 winds and temperature for everybody to focus on about 30 hours into the forecast. It's subtle. Actually, I'm going to zoom in just so we can easily see these maps. Okay, so in this forecast, this is in the NAM. You can see that there is, the strongest frontogenesis is to the south. It's clearly to the south here. Before this time period, if I go back a little bit, 48 hours, this is what the NAM had us getting some rainfall. It actually doesn't really show up that well here in terms of the NAM forecast. If you look at the winds, there's a slight turning to the wind as you go into the warmer air, but it's not as prominent. Yeah. But the NAM was actually producing some precipitation over us, which is kind of an interesting aspect of this. There's a little bit more evidence, I hate to say it, but in the GFS in terms of the frontogenesis. So this is something that's a little bit peculiar in the forecast. I was looking at this earlier, and it's like I have a story to tell that's interesting, but I may have gotten the maps mixed up. This is at 700 millibars, and there is certainly confluence here, but the temperature structure isn't necessarily the greatest one to produce precipitate to produce frontogenesis. But there is confluence, and we do have cold air to the northwest, warmer air to the south, and we did have the dew points being pulled over our area. So this does suggest at least the place to look for some of the chronogenetical elements are probably going to be over the in the NAM at 700 millibars. You just don't want to look at one level in particular. So there is a bit of confluence, but it's not the most obvious setup for rainfall for us. If you go to the GFS at the same map time, and at least there's consistency here, there is weak confluence, but it's weaker here than it was in the NAM. So I'd argue that it's weak mid-level or low, 700 millibar frontogenesis. That's the close for the precipitation that we're going to be getting. John, if you have any comments on that diagnosis,
I think that's right. I think you're looking at the right elements. I would have done the same. I think that it's weak, and there are times in the year where weak confluent frontogenesis or weak, maybe even less, shear frontogenesis can give you a reasonable shot at precipitation. One of the interesting things about the evolution that leads up to the period where you're diagnosing the confluence is that, when you have a lee side trough as the origin of your warm air, that air is a little bit desiccated compared to what might be there in a normal situation. And it's curious that in all the models, only those air parcels that arrive at much higher northern latitudes, and I'm thinking this is because they have a longer period of time to moisten up, are the ones that actually end up precipitating. So it really is it's a numbers game for us. We just might not have sufficiently long enough time for those air parcels that arrive over us when the confluence arrives over us to have moistened enough. And the models seem to disagree a little bit on that fact, but that might be what underlies it.
Yeah, if you look, when you were showing the maps for the superpeat maps in the lower troposphere, you could see there were dew point depressions on the order of 20 degrees Celsius over the central plain. So that air is going to have to rise a huge distance before it is capable of condensing and producing precipitation.
Yeah, I think North Platte had a 28-degree dew point depression and a temperature of 27. So that's not going to precipitate till it gets to northern Hudson Bay.
Right. And so the last thing I would get over, but I just want to take you through this in terms of the evolution of the flow. We saw that we're going to get this ridge developing over the west coast and a trough in the central part of the U.S. You can see the cold front comes in. Here's the cold air. Thickness trough shows up pretty well. You get chilly, you get even chillier with the next development. This is when we get to our next weekend. And then we get these really intense cyclones developing over us with periods of cold air coming in. But we're headed toward fall, and looks like we're going to be lying along a baroclinic zone that, for most of the time over the next 2 weeks will probably be just to our north. But next week certainly will be a chilly week with temperatures only in the 50s as this trough begins to amplify over us. And then after that, the weather gets a bit more progressive in terms of the changes of it. But that's a nice cyclone.
That's an Alberta clipper, isn't it?
Yeah, these are right. These are exactly. This is the fall, the winter pattern that's showing up. Unfortunately, we're not getting snow from that. But a great setup. John would love that.
We do have some hints of little convective straggling showers on the backside of these storms, like this right here at 540 thickness. Temperature is at 850, is like +1 or -1. So they're not going to snow, but they're going to come darn close.
Yeah, you could get a little bit of some ice pellets or something in that, or grapple if you get a little bit of hail. Maybe. In that. Awesome. So that's going to be an interesting setup. And I'll leave the extended for another time. But anyway, thanks for your attention. Again, the weekend looks relatively warm. The question is going to be about precipitation. Will we get much of it? But the threat starts from late tomorrow evening with an approach of that front. And then during the day Sunday, I think it's going to be, we might see a brief shower as the cold air begins to come in, but it's not going to be a sustained washout, I think, by any stretch. And then we just slowly turn colder over the course of the week. So thanks again for your attention, and that's it for now.
Thank you, Michael. Thank you, Greg, and thank you, Pete.
Okay, 141 class will meet at 1:20.